to cause surface uplift. Sources, to move material, have condensation. And of course, all these surface processes, they're all interconnected. This makes it a very complex system. To see what kind of parameters that can actually change to have a certain effect in the development of the landscape with economic values. About 10 years ago, now 2018, or 8 years ago, Antonelli and co-authors published a paper in Nature Geosciences, where they were looking into these aspects of linking mountain building and mountain biodiversity. They were saying mountain belts only represent about 1/10 of the Earth's surface. If you look at the ones that are exposed for continents, we're not looking at the southwest ones at this stage. But they hold already a quarter of the terrestrial species. So that really shows why mountains are hotspots for biodiversity. They're very rich in species. This phenomenon is probably related, they were saying, surface uplift, raise the surface because of tectonic processes, climate variability, climate change, and atmospheric circulation through time. Atmospheric circulation, of course, is important for the redistribution of heat and moisture. For our planet, and it also goes associated with this, of course, all the different climate zones that we have, tropical regions with temperate climates, desert climates. So to better understand this link between mountain building and biodiversity that we find in these areas, I think we have to get a better understanding how the biosphere and the lithosphere actually interact. The surface of the Earth is pattern. So we have to get better understanding. One of the main challenges in this is to get two groups of researchers together, biologists and geologists, to try to communicate, which in the first place is not easy because we don't speak the same language necessarily. We don't have the same terminology, and definitely don't have the same concept of time. There's a couple of processes that are important on the biological side for controlling biodiversity. I'm not going to go into the detail that we did most likely. Simplified, there are four main processes that will control biodiversity. Speciation, basically evolutionary formation of new species, usually by the division of a single ancestral species into two genetically different daughter species. When these species are formed, then they disperse them. They can move around, or they can be animal species, birds can fly, and animals can move around. Plants, of course, will disperse by dispersing their seeds or their pollen. Then, so basically, they move beyond their original area where they have formed. And this is very important because you see that these species are very dynamic. The persistence, basically the capacity of these species to adapt to changes in the environment, to climatic changes or habitat conditions. It could be on a very local scale, because of a landslide, maybe local conditions that change for certain species, how do they adapt, and if they can adapt, or on regional aspects. And then, of course, also over different time scales, millions of years or only days, weeks, centuries. It can be extremely critical. So this adaptation could be either because they evolve, the climate is changing, and only the ones that have the capacity to adapt to the newer temperature conditions can survive. Or if they can migrate. If they're not happy with the conditions, they will try to get to a place where they can actually find the ideal temperature and precipitation. And finally, those who cannot adapt, if the conditions are changing. So global disappearance of a species or a population is that to extinction. And when all of these members are within the text and life. So these are the four main biological processes that will be important for biodiversity. And we have to see how we can factor this into all the geological aspects. Just a word on the species themselves. There are different definitions in biology that exist, different definitions for species. The one that is usually used is this biological species concept. Basically, The species is a set of interbreeding organisms, the ones that can reproduce offspring. This would be considered as a species. An endemic species, this is of course a species that is a taxon that is geographically restricted to a certain area or region. So that was the term endemic to be used in connection with the region. So a species endemic to the Alps, endemic to the Andes, endemic to Eastern Cordillera, or whatever. It's restricted to this particular investment. So speciation again, evolutionary formation of new species. This is of course also that associated with macroevolution and microevolution. This is where it becomes interesting for us, because when we look at which times there is macro or microevolution in the world, this is where we can link these to the tectonic evolution of mountains. So for example here, macroevolution processes take place at or above the species level. It's good. And using bonding time scales of millions of years. Evolution of Homo sapiens or many other species that are on that time scale. Microevolution on the other side is much faster, so that will much lower some levels, so sometimes even below the species level, within or among a population of the same species. And usually bonding time scale is shorter than million years. Now we have to see with what kind of geological behavior techniques, for example, we could constrain these time scales. This is usually expressed in a number of generations. Okay, so if you look now at an environment and think, okay, what is biodiversity? And there, biologists also have different terms: alpha, beta, gamma, diversity. If I look at a model here for the Alps, where we have the different vegetation zones, foothill zones, montane, subalpine, and then the alpine zone above the tree line, and then the snow zone, that there's only most one in it. You can see some examples of trees, right, that grow in these areas, what kind of resistance they have to actually the winter temperatures. What kind of cold temperatures they can resist. And you can see that, of course, shown in this cartoon, that we're changing basic deciduous forests to mixed forests into evergreen forests because they are more resistant against the cold temperatures. And at the moment, the tree line is about 2,200, 2,000 meters elevation in the Alps. But this is starting to move up. You can see the global warming trend, but there's already trees starting to grow above current tree line. And you can also see that, of course, depending on the exposures to the south and to the north, of course, warmer conditions on the southern side and colder on the northern side. This is why the elevation is not exactly the same on both sides of it. The other thing you can see here is the length of growing season. It was getting shorter at the higher up. We all know there's a certain mountain rate that's roughly about 5 degrees Celsius per kilometer. You go back to the Antonelli paper. They were showing there, if you want to look now at alpha biodiversity, is basically we look at a small area here, and biologists count, okay, how many different species of plants, or insects, or whatever they want to look at, is living in that area. That would be the species regions over this small area. Then we can go up the mountain side. We can look at how does the species richness in this one mountain range or one mountain actually changing with elevation. Usually the warmer the conditions, lower. You have a higher biodiversity. And the higher up it goes, you have the species become more specialized to resist the colder conditions. So we can compare all these areas, that will be then the better diversity. Basically, we look at the changes in species richness and composition from one small area to the other. So this is very good for very local, maybe regional studies. But what we usually look at, I will show you a second, is what's called the gamma diversity, which is the number of species over large areas. Okay, we'll come back to this gamma diversity. So what controls or what is important for the dynamics of these species now to gamma diversity? The one is, of course, migration of the species that we had mentioned before. So they're trying to adapt maybe to changes in climate. And there is, of course, once the boundaries can be both. They can be barrier to migration. They can also be a pathway, a corridor for migration. Depends on the specifications of the species that we have. So if you imagine we have plant species that are trying to migrate from one area to the other. This is an example of the Western Alps, Grenoble is down here. In this direction, the species would have to mount, of course, an elevation, but to get across the mountains if they want to get to the pole basically on the other side. This is for many species impossible because they would have to go into temperature ranges where they cannot survive. On the other side, so this would be a barrier for migration in this direction. On the other side, the north-south migration is possible because then the species can basically stay in the elevation for the most part as they need for. This is very well known. The migration that is happening in Panama to South America. This was in both directions actually, because then the species could migrate along this corridor. Yeah. Mountains can function as both species barriers, but also as corridors for migration. And also the river valleys, there are long river valleys that go into the mountains. The species can also, of course, migrate to a certain part or certain level into the mountains. So there's this aspect. The other aspect is what they call sky islands. So you can imagine this is one thing that comes from the book of Karina Horn, in the chapter of Natura and Policy stuff, where they show if we have a certain mountain topography. You can imagine now we topography over like interglacial timescales is not changing a lot. We still have some peaks, we have valleys. You can imagine that if you have cooler climatic conditions, a certain species may be all along this lower part, so they can migrate easily here from left to right. However, if the conditions change, like we experienced before, with global warming, these cold-loving species have to move around the mountain to stay in a temperature range where they are comfortable. They basically get trapped in what we call the sky islands because there's no longer connection here during these warm climate conditions. If the climate changes afterwards, becomes colder again, these species will migrate down and then reconnect to the others. But it could happen that during this time that they're up here on the sky islands, depending on how much time it takes, they really evolve. So here there were maybe the same species that became trapped in these sky islands. They evolve differently, and then they migrate back down and mix again. So this can be basically with the change in climate, it's become a species problem. The climate conditions just change. Regarding the morphology, the problem is so the ecologically dissimilar areas around the mountaintops, of course, that serve as a barrier. Just physically, they cannot communicate during this time that they are. So we have this horizontal migration, and we have vertical migration in the mountains, depending on the climate. So there we can ask the question: one of the things that we have been starting to work on is which geological factors may have an influence on speciation. Do we have times of geological events that can actually trigger speciation events or control dispersion or influence the persistence or extinction of these species? And if so, on which timescales? And how is the evolution of biodiversity spatially and temporally linked to the tectonic evolution of mountains? On the timescales, and which role plays in fact really the climate variability? Okay. I have shown you the thing with the mountain tops. Let's get also another example for these sky islands. It's during really cold conditions. Because there I talked about warm or colder, warm. So other extreme, like in this case, Antarctica, but imagine during the main glaciations, then between 20 and 17,000 years ago, large parts of the Alps looked like this. We only had some mountaintops sticking out. This is what could be a refuge. Some species, some little plants, or some lichens, some finding refuge in these mountain tops where there was outside of the ice. Basically sitting there and waiting until conditions change again. So that they can find them. So the refuge is also another kind of concept. And then we have currently a project of this colleagues from the ecology group and we're specializing on the refuge kind of species that they want to study. Okay. Coming back to the actuality paper. So here you have this global gamma biodiversity map where you can see the species richness. In this case, it's vertebrate species that they had selected for this to make this map. So basically, amphibians, birds, mammals. When we look around, and of course, we can see, which is not a surprise, that we have a very high biodiversity here in South America, and particularly not only, of course, in the Amazon, but also along the Andes. You can see this also, of course, here in the East African Pacific system, Africa, some other parts. And of course, you can also see the areas where there's extreme low species richness, where there's a lack of water. We have these big deserts, and really large parts here, of course, in Australia, of course, the Sahara Desert, and of course also in the polar regions. So species diversity hotspots are related to elevated mean annual temperatures and abundant precipitation. Water needs warm and water is absolutely key. And also important topographic relief. The more relief we have, more basically ecological niches we can find. So with mountains, the species really correlate with the erosion rates and heterogeneity of soil types. This is one of the things that they found out at their study. That basically the possibility to create soil, but also eroding and expose fresh water and so on, that creates a ruggedness in the relief that is very complex. And the more complex, the more heterogeneity we have the topography, the more new habitats we can form, can be exploited by the species, plant species or animal species. And so also, of course, these new habitats, the erosion of the rock, transport of the sediment, but also with the species are basically distributing nutrients to the lower land areas and carried out across the land rivers. So in that study, Antonelli and co-authors, they were looking at a couple of different parameters. So they basically wanted that shown here on the slide before. They were looking at the geological ones on relief, long-term erosion rate over millions of years, what they call erosion potential, basically how easy it is to erode the rocks, and the soils that are developing. And the climatic factors, of course, precipitation, temperature, the temperature range. Basically, if it's American climate, it's a continental climate, it's tropical, it's the Arctic, etc. And also the basically the seasons. What they found is that if you look always against species richness given here, and the annual precipitation. There was, of course, a certain relationship also with the mean annual temperature, relatively good relationship, and also the temperature range. Then they have also been looking at the mean local elevation range, so basically the relief, the long-term erosion rate, and the number of soil types. Well, there it's relatively broad that the strength of types. What is interesting, if you look at this lot of different areas, of course, this is a bit limited to the data that was available to them. For Africa, for example, this whole region here, there's since there not enough information in there for them to include in their study. So, and for the Andes, it's also, well, they basically put everything together. The northern Andes, the central, and the southern Andes. It's a very kind of global view. Some areas would be good to look this more regional. But what I wanted to point out is depending, as you can see with these graphics down here, depending where you go, you not always have the same parameters that are important for the biodiversity. For example, here they were saying this temperature is very important, precipitation, And this is here for basically the Rocky Mountains and parts of Central America. Relief is very important, so are not the erosion rates. On the other side, where I look here in Australia, this parts, again, precipitation temperature is very important. The local relief is important, but also the long-term erosion in a certain aspect. Or if you go to the Alps, the temperature of the precipitation was less, it was more the temperature range, not the continentality of the climate that they grow. And also the sulfur tension. And here in the ends, of course, very much the precipitation temperature and the so with these graphics, you can see that depending on where we are, what kind of climate conditions, mountain belts, and so on, it's not always the same factors. There are regional differences of which factors are open points. Okay. So let's focus on the Alps. And there's a Northern. This is, see, the Alps are fairly small mountain belt compared to the Northern Andes, but we have 3 mountain belts here, there's just 1. You can see the highest point is Mont Blanc is 4,808 meters. It's shrinking a little bit because it's losing its snow cover, especially the temperatures that we had recently at 42 degrees. The valleys, so you can imagine it's too hot to keep eyes on there. So one day the Mont Blanc, the white mountain, will become a gray mountain because the ice will be on. But at any rate, you can see the curvature of this mountain that is associated, of course, with plate tectonics. Is the collision of this Adriatic microplate with the European plate basically colliding. You can see in this graph here the Atlantic plate has been shoved over the European plate. It's been subducted beneath the Adriatic. And this whole African, Italian, basically considers here kind of rotating. This is why we get this kind of curved shape of the mountain. When you look at the distribution of precipitation, of course, the Alps get their fair share of the precipitation. You can imagine all the air mass that come from the Atlantic. You can easily see, of course, it's raining along the coasts, where you have the first time it hits the coast, then it moves over. Basically, if we just look at France here, the Paris Basin being fairly dry, then it hits the mountains. The air masses on the parasite to move up, they lose their capacity, and they cool down. This capacity of the carrying moisture starts raining, very typical orographic precipitation. And in Colombia, we have about 1,000 millimeters per year of precipitation, which is not outrageous, but at least sufficient so far for maintaining the vegetation over there. Although the last 3 months it has basically not worked. If you look at the temperature map, and this is a bit old by now, it's about 99, but you can see nicely that the valleys here, the glacial valleys that are carved out during the last glaciations, are basically warm air corridors that go into the mountain. You can see this also here across on the Italian side, basically where all big lakes are. These valleys were all carved by glaciers. And they have low topography, of course. Bottom of the valley, this is where the warm air can go into the mountain. But generally, we have, of course, warmer conditions to the south and cooler to the north. Nonetheless, this is mainly east-west oriented mountain belt, so you can get times of precipitation on both sides throughout the year. It's not that there's a really dry side and a really wet side, no, it can be variable. This is a bit shown here by the precipitation map. Geologically, we have basically everything that is what's called the internal Alps here. This is basically the light blue, well, the limit of this is here along this line where the light blue gets the green and the reddish colors. And in red, what we see is what we call the external crystalline massives. These are crystalline rocks of European plate. They are now they have been exhumed to the surface. They form the high topography here in the Western. From the biodiversity point of view, this for European standards is good biodiversity, but not much compared to here. 4,500 species of western plants, over 5,000 species of fungi, mosses, and lichens, particularly of course. 400 land species that are endemic to the Alps, or considered endemic. About 30,000 animal species and about 80 mammal species that we found at this stage. Okay, so why do we do this? This is of course the thermochronology. This is to use thermochronology to understand how the mountains have exuded over time. And I'm not going to go into great detail in this talk. It's just thermochronology, for those of you who are not that familiar with it, is basically a technique to determine time and temperature. Because these dating techniques that we don't use, vision direct dating or rain therapy, of zircon and apatite, there are sensitive to different temperatures that we call the closure temperatures. And if you have a rock in the deep crust that is high surface temperatures, high temperatures, when it gets exuded to the surface, it will cool down because the surface temperatures will go lower than the deep down crust. And during this exhumation path, it will pass through the different isotops, these different thermochronometers, and it will record basically the cooling history of this rock. We can collect samples along the relief, we call elevation profile, that are studied locally at this location, what was the exhumation history. Or we can also look for river samples, modern river samples, where the river basically is sampling drainage area for us and mix all these amatites and serpents in and analyze those. You can see what kind of signal do we have and use this to estimate exhumation rates. And we can also, of course, use samples from the basin, if the basin is still active or it has been converted, and analyze those samples and see what is the long-term history of exhumation of these things. So the answer, of course, that mountain that has been extremely well studied over the last 150 years. Since the 1960s, people have been using vision direct data. Here you see a combination of several vision direct images. They published in 2023 over the years. And the color coding is that you have the Jurassic ages more like here, really taste bluish, and then the more recent ones, of course, everything that's like considered as alpine orogenic, which is younger, still 5 million years, is the orangey colors. There's an interesting trend that you can see here in this part of the Western Alps, where you can see a color trend from bluish to these pinkish colors, which shows that we had the exhumation history, the collision that started really, continental started about 35 million years ago. And this has been propagating to the west this age. And with this also the crows are pretty. So we have been doing, of course, different series of studies in these mountains. You can see on this map here, there's a map that shows different metamorphic rate of internal Alps. Then you see the black line here, which is the thrust front, it's called the pinning front. And then the outside is for European part. So there are two studies we've been done. The red square here, the study that we published in 2015, where we've been looking at this evolution of this part of the Alps, which is shown basically in this cartoon, where we had to come up to this conclusion at the time that there was high elevation already about 30 million years ago in this part of the Western Alps. With the Western Alps. Basically, since later on, similar to the elevation that we find. And this was based actually on pollen analysis. So we had looked at pollen deposits, well, not me, our colleagues from Montpellier were experts for this. They had looked at different locations here and seen what kind of pollen species do they find, what kind of pollen sandwiches, and to which kind of vegetation belts that correspond. They were looking, of course, what are the vegetation belts we have today, and which elevation are they, and then see what kind of, if they found, for example, beechwood, or deciduous trees, etc., or evergreens, that could indicate specifically these Larix and Pinus several. These are species that we can high elevation. We find something like this, there has to be a certain mean elevation peaks to allow these species to exist without us. Particularly considering that till mice and mid-mice require a lot of conditions to actually warm up. So these species kind of be in the higher up. So on this, based on these pollen studies, we found that this part here, the elevation was probably because we find these high elevation sandwiches in these Oligocene sediments that the mounds were big. Then we've been looking up in the bit further to the north here in the Western Alps around the global. We have been looking at the exhumation of these external crystalline masses. And here's this in front. There's the limit, the internal. So we have to see, okay, when did this mound actually become exhumed, exposed the crystalline rocks at the surface? Because it has an important impact. Everything is in blue and green here. These are the cover rocks, and they're all sedimentary, mainly carbon rocks. And eventually we start to exhume silicic rocks. It means the soil types that will form will also change. It has a big impact on many species. Certain land species can live with river soil, others are very specialized. So a lot of work has been going into these exhumation of these crystalline rocks. And this is some work that goes back to two studies. Christoph Klotzbach studied in Mont Blanc, which is sort of this gray fishing track data here. This is the surface fishing track, where you see the fishing track age as the elevation. And then also in the Laniège, which was an older study by Peter van der Velde. And then what Jean-Baptiste Giron did for his PhD thesis in parts of the Belledonne Message. So what we can see actually, we see this break in slope here in these certain fishing track cooling ages. So again, this was sands that are collected at different elevations. We can see older ages here, what we would expect, rocks that are higher up, cool to earlier, ones that are more valley. But we can see that there was a trend from probably Paleolithic, so here that has been exhumed at about 15, 16 billion years, because here the age starts to align more or less about that time. And we see that in the Mont Blanc, a similar trend, even higher up, but it's younger. That's more like 10, 12 million years. So it means between this part here, the Belledonne and the Mont Blanc that is up here, the timing of the exhumation is not exactly the same. It's all limestone, but it's not talent. What we also have been doing is we've been looking at the deformation in the foreland. This greenish units, which are called Gauche Atreus, this is what we call the subalpine chains. This is basically sedimentary copper units still that have been strongly deformed, short, thrusting at the ground. There, we had two PhD students, Antonio Bilot and Dorian Villareno, who have been working on this. They have been doing regular dating of calcite on fault zones. They want to look when was the last time these major thrust faults here were actually activated. With the regular dating, they could do this. And what is interesting, here the Belledonne message is exhumed at about 15, 16 million years ago. And we see the continuation of the deformation. The first thrust fault here about 15 million years, 12 and 8. And actually, there's another one at 4 million years, which is the sequence thrust here, that had been reactivated. But after 4 million years, you don't see any deformation in this area. It's probably a kind of stop there. So we have this pulse of exhumation here and propagation of deformation towards the west until at least. Do we know that during that time, this topography there? We've also been looking at pollen in these sediments, in Miocene sediments, from about 10 to 9 million years, about 80 million years ago. And it's interesting, in these pollen samples here, we already find at 80 million years high elevated species that indicate there must have been high elevation in the Western Alps, probably by that 18 million years, which is a bit later. Minimum, because for the southern part we said it's about 30 million years. Here at least we find evidence from at least 18 million years that was high elevation. We looked at the granite pebbles that have been shed into the foreland. There was associated with exhumation of these crystalline rocks. They those with red dating, and also with fishing track dating. And for the fishing track dating of these 18 million year sediments, but we know that there was high elevation. We also can determine exhumation erosion rates, which are on the range of about 0.5 kilometers per meter, about 500, which is similar to what we see today in the rivers as well. So there's been a continuous erosion cycle of material in the way. So the first arrival of these granite members at that time as well, which basically, well, you've seen from the age of Asian data, it's at 15, 16, by 18 probably already started to remove the cover limits until the age signal arrived. They became very aggressive in this deposition of these pebbles from 12 million years old. This basically when the deformation also had then when moved into the form. So now we wanted to see, okay, how did this now influence the biology of the biodiversity? This was worked out by Laura Gould. She was a PhD student at laboratory of alpine ecology. And she was only focusing on the species, the plant species that are above the tree line, that really need higher elevation. And she wanted to see, okay, what kind of biodiversity do we find there today? There's been a lot of work done by others before, so she was compiling all the DNA data and so on, because they used DNA sequencing to get a temporal evolution of this development. And of course, there are different processes, as we had mentioned before. Basically, new happens that species are migrating in because of service others creating rock because of climate variability, and also because of connectivity, this possibility to migrate with other species. Because they have been connected or they become disconnected, isolated here in these sky islands. So there's different species, but also the possibility we have a species that moves in from the outside, and once it has arrived, starts actually speciating. They have first colonization and then basically splitting up into new species. So it gets relatively complex. So they have a very large database that exists, over 6 million georeference samples that they have, for which they have, for a large part now, the DNA analysis. So this is basically very international kind of collaborations. But you can also see that here the species rich information is much denser than maybe other parts of the Alps, as always. And they wanted to know, of course, with their models, especially when do we have the common ancestors? And what is very important in this kind of work is to find some fossils of these common ancestors. To actually tie this in, this is where stratigraphy becomes important. And they find fossil in the sedimentary rocks of the fallen basin. Okay, what kind of structure of age do we put on this? And from there, they try to model them with their DNA analysis. Okay, how much of the DNA is in common between these ancestor species to get to certain targets. This is where we try to relate, based on these regions, try to relate this with tectonic events that we have in the Alps. So to make a long story short, what Laura found is this is the development of the species richness that we observe nowadays in these zones above the tree line. And I had shown you with the tectonics that we had probably high elevation before because of the data. But what she finds by looking at these present day species and do the DNA analysis on those, so there's little evidence of sky island villages before 7 million years. The accelerated during the Pleistocene. This is when we see basically a huge increase in biodiversity. This is because the lineages increase up. It basically contradicts the results of what previous studies had said. There was basically, so you did not find any initial, any relating between the initial surface levels and the assembly that we see nowadays. So we have high mountains and we have a topography, but the signal that we see today is very recent, the last couple of years. And what is probably the reason for this is the intensification of glacial climate, interclimates changing over the last 2 years several times. So it's possible that we have higher biodiversity before, but they're extinct, and there's no trace left in the fossil record. So from what is existing today, you can only see this very strong case. The other thing that is interesting is where's the origin of these species that we find in groups? For a large part, the majority, actually, not all, so many interesting. About 261 of these species are coming somewhere from Europe, another 100 that are more like from Eurasia, some of them 100 about from the Mediterranean, from the Northern Plate, another 100, and then Asia, for example, maybe even eating from North America. You ask exactly, how did they get over there to the Alps? This is not because they were brought in by humans now. These are species that have been around for a long time. So of these 1,100 species that they looked at, it becomes very complex. But it also shows how important this migration of these species is. Because this is over the last 2 million years, since we see this explosion. And with these glaciations, which are playing on the 10th of thousands of years to 100,000 years timescales, these species basically during glaciation they move out to lower elevations, and then when the climate runs up, so they zoom back in. And this is what we can at the moment observe that they're new, what they call invasive species, they move up and come in. And one of the species that I can always personally control is cicadas. Cicadas resemble the sound. This is something that when I first arrived in France 20 years ago, you could only hear the Provence where it's really more. Now we have in Cologne, when you're morning, you can hear them, especially when it's so warm. So these are species that have been moving from the north a few hundred kilometers within a few weeks. So this is super high hectoscope. You can show this relationship where we have our tectonic events. We already see that there's high elevation species in the past, but the pollen analysis is not on the same level information as we do with the DNA analysis. And then there's this really strong increase that is left by the glaciations, which is fun because it's actually not the glaciations themselves, it's this rapid change. So basically, the species move up and down the mountainside. It makes sense. So species speciation is based on the DNA sequence of alpine zone plants that live on the over 2,000 something meters. So minimum of the elevation is probably the only difference that the present day biodiversity is driven by these glaciations. The impact of these glaciations we don't know because of lack of fossils. We can't really say how that was this is basically to find discoveries. This is the most challenging part of this type of studies, is to find these ancestor species in the fossil record. So if you look at this in the Alps, the Northern Alps, so imagine do something similar here, where we have, of course, the same model what I showed you before with the Alps. We found out not consistent 74. Of course, the lowlands, savannas, the lower tropical forest, the submarine forests, and deep forests, and the paramount. So the paramount would, of course, correspond to, you say, the alpine sort of tree line. You all know how important the paramounts are in the Arctic. These tropical wetlands with deep soils, rich organic matter, control the water flow. And of course, there's the really famous and fantastic species of Escarpment, which are endemic to the Arctic. So this is a study that was done also by our colleagues from Leka a few years ago, where they basically were showing here on these maps where do we have these parallels, where do we have these escarpment purity in these mountains. And so basically coming back to this concept there of with these changes in climate. When you look at the Pleistocene climate fertility that we had, super close on this model, basically the same what we see in the Alps. You can imagine here on the Andes as well, with this variability, pump up and down these species, they get isolated, they change, they come back, they remix. This can do, of course, a very high increase in species. So this is just a model, but to show you these different processes, like the fragmentation, because there are species here that are common, they get fragmented with sky items that can develop differently, by maybe 3 new species at all. Then you have the colonization possibility with changing climate. It's species that move around. You have the intermixing, and they reconnect. They will form new species because they intermix in these areas and then redistribute, or they will actually do hybridization with the species. So all these processes will help to increase this biodiversity. So they have been modeling this, what we call the mountain fingerprint, for cold climates, for warm climates, and see how maybe what kind of processes could have taken place. But this is more kind of a conceptual study than really based on specific species. And I find it interesting when I found this study from Bouchon and from colleagues from the Lika is when they look at the esprit-based species, and we identified very different types of those, in Maria particularly, but also in some other massive this one species here, which is this one here, that that exists, and some others around the Kukui in other parts of the park. Their study was focused more here in Merida at the time. So when we look at the evolution of these SPT, we look at the tectonic evolution, for example, the Santander, this is where we found in the many others here over the last decade. That we now recently published this a book that is coming out of the Geological Society of London Special Publications. We have published about others, others. When we look at the Santander Basin, we have the Bokono Fault coming up here. We have what we consider as the western block and the eastern block. We know that the Bucaramanga Fault is a strike still fault, a very strong vertical component. We know that the elevations here will get easily over 3,000 meter elevation into the Paramo. And on this side, it's much lower, only about 7,000. We look at the surface fission track data here. We can see, of course, further away from the fall, the ages become older, but along the fault, they get very young, down to about 25 million years. So we see within the fault zone here. See, this is to basically to the east and to the west of the fault zone. The western block, we have this lower elevation, older ages. Then on the other side, we have really only seen what we call it super, so really young ages here that show the moment of the spectrum 25 years. If you look at the Eastern Cordillera, there's a nice data set from Maurice Meyer, and he did his PhD in Potsdam, Germany. So it was published in 2009. We had fission tract ages, certain fission tract ages from the down massive and from these Cretaceous, lower Cretaceous seeds here. And you can see the older ages, and they get really young here within the Gitano massive, and the crystal rocks that show very deep level. The signal is a bit more complicated because it has been dissected by these rough faults. But if you plot that basically on the an age elevation trend, you can see in some of the this combines with more data in this profile. You can see a very strong signal here, about 15 million years of cooling, 10 and 18, roughly. On this scale, of course, it's been compressed. And then we have the signal, and then the older ages are here because it's dissected with these thrust forms. But if you look at the Santander massive signal that I just showed you before, we have this exhalation event at 25. So there's a time difference. It clearly shows that the exhalation there is strongly controlled by the counts. This area. So we have a 15 million year basically exhalation event. You can see on this side in the circumfish data. We know from other things that the main uplift, of course, of the Eastern Cordillera was later, times in months. But there is tectonic events that can be 25 million years in the Santander. Work that we have been done in the Merida and this for Maurizio Bermuda's PhD thesis, then we found exhalation events from 40 pulses of 40 million years, so very similar to the Eastern Cordillera, and up to about 2.5 million years. But this is different blocks within the Marianas that are concerned about this events. Anyway, why haven't we tried out to link this to the biodiversity or occasionally SPT? This is the phylogeny of SPT that was published by Bouchon, and based on their DNA sequencing that they've been doing on the SPA and the couple of fossils that they have found to tie this in, they say the original species, these from the ones that they had done here, we go back in time. So it started around about 30 million years ago. Then we have events where they start to split up. There's an event that's about 25 million years. There's another one with major speciation at about 15 million years. So we can ask, well, there's a relationship now actually between these tectonic events that we see in the thermology data and with the speciation, not one here, 2.3. Or is it just a coincidence? This may be the other, because we have to test it with other species. We have to do this on other kind of species. The Spinea are great because they adjust the curve here. Endemic species are, of course, the best way to do this. I talked to the people of the lake, but they said, no, I took this another thing, so we don't want to go back into dealing with the new species because it's the same outlook to this. But one proposition we could maybe think of, let's look at other parables around here, look at other species, and particularly my colleagues there in the lake, I think Chemisona could be a good target species to look at. It's a bit more complex than the SPA, they also occur at a larger elevation range. Other thing could be maybe mosses. They look at moss and try to see if there are specific ones there. But for that, you would need, of course, the help of biologists because this is only my expertise in country. But there could be, maybe targets to look at and see. Do we see the same events of speciation, or do they show something? So far, I do not have answers. But anyway, when this kind of research continues, we try to really integrate into information that we get from biological side, biosequencing, plant species, the polymer sandwiches from the old samples, the fossils that we found, the thermochronology that we can do on timing on the trajectories. Then try to basically diverge times from the species and the erosion rates, the tectonic again, put this into landscape evolution lines. Of course, the objective to see, basically model the present day topography, see how we get to this, what kind of parameters and the time of this. And you can see already that needs the collaboration of really different experts to do this. And in the answer at the moment, there's one project we have continuing, and we mainly focus on these zones again, particularly in these refuge areas of few species. So coming back, which geological factors may have influence on speciation zone, the question we asked. Well, on a regional scale, the mountain, the rise of mountain that's over several tens of millions of years. They will affect the species by distributing and operating migration pathways, disrupting the pathways, and the formation of new habitats. More topography have, the more complex the topography, the more habits. On a local scale and shorter time scales, years to thousands of years, the surface erosion, landslide, river dynamics, and volcanic activity can actually isolate species, can cause local extinctions. But a local extinction usually is an area barren for other species to move in and to repopulate and to use. And then also these things can of course create new habitats for colonization as well. So it stays very complex. So how is the evolution of biodiversity, spatial and temporal linked to the target group? Well, from what we see so far from our other studies, the mound building basically sets the stage for creating mounds by topography, but the biodiversity is very quickly developing. So it's basically creating the geological background that the species have their niches, their space to develop. And climate variability is basically a major driver force for species extinction, migration, isolation, or this is of course water temperature under control of these species can adapt and move around, including ourselves. And with this, so thank you for your attention. Vamos, nos tiempo para preguntas.
Sí, profe, una pregunta que te tenía.
Sí, sí, claro, por favor.
Tú presentabas de los antes del oeste, ¿cierto?
Sí, yo voy, sí.
Comentabas ahí que me llamó mucho la atención que en los últimos 18 millones de años, ¿sí?
Sí,
La altura promedio era muy parecida a la de ahora.
sí, eso es que pensemos, con las, mínimo, las estimaciones que tenemos, que, bueno, inicialmente tuvo más relieve acá, y con el tiempo hicimos la surrección acá con la deformación que estoy contando del oriente al occidente. ¿Sí? Y la estimación es que mínimo por los últimos 18 millones de años, el promedio de la altura no ha cambiado mucho. Individualmente, claro, tenemos con las glaciaciones, hicimos los últimos 2 millones, las fachas que tuvieron en ríos antes, ahora son más grandes, o después los que nos pasan, tenemos más erosión. Entonces, tenemos una amplificación del relieve. Pero eso es como los modelos que estuve demostrando la semana pasada, que si hacemos como más erosión, tenemos también más compensación. Obviamente tenemos algunas picos que son más altos, pero en promedio la altura no necesariamente cambia mucho. Esa es un poco la idea. Pero también en el problema que tenemos. Cuando hicimos este estudio más al sur, tuvimos más posibilidades de encontrar polen en los elementos oligoceno, mioceno. En esta parte, tenemos un gran tipo megafauna acá. Porque son muchas muestras, casi nada. Solamente estas dos muestras que funcionan y tienen alguna congresia. Desafortunadamente, esto es muy importante para saber. Es posible que tuvimos una subvención antes, mínimo en esta parte claramente, pero no podemos ver en los elementos acá, solamente más al sur, que tienen algunas formas que para mí corresponden la altura de su cosa. La verdad es complejo, es difícil, y si no hay los depósitos antiguos, los fósiles, las empresas del pasado. Y la otra cosa es que no tenemos hasta ahora muchos estudios de paleoaltura. Estuvimos hablando la semana pasada sobre diferentes métodos que existen, como oxígeno, el oxígeno, los isótopos de oxígeno, las plantas, hablando de este estudio que dicen la forma de las hojas, como esa, hasta ahora esto no existe, ¿no? No tenemos buenas otras indicadores de la altura del pasado. Es muy difícil. Y acá en los Andes, como puede ser también bastante difícil de encontrar fósiles que necesitamos para hacer como un contraste, por ejemplo. Podemos probar. Pero,
cuando se datan los sedimentos, se data la fecha en la cual ese sedimento se formó en la montaña, o a partir de cuando se erosionó de la montaña y se depositó en el terreno.
hacemos diferentes cosas. Normalmente las edades de depósito de los sedimentos son hechos para manejo geográfico o para biozonas de microfósiles. Eso es como, por la terminología, yo puedo con la terminología, si yo tengo muestras acá de los sedimentos, yo hago análisis acá, pero saber cómo está la expresión de la montaña, por hacer integración del tiempo de la carga enfriada, expresión de la superficie, la versión, transporte y depósito. Este puede utilizar para calcular qué es la velocidad de este objeto. No me dicen que es el depósito. Si yo tengo capas botánicas, sí, voy a tratar de ver las capas botánicas. Y verdad, eso está súper bien mantener como la teoría. Pero los datos no tenemos. Entonces, vamos a trabajar con los centros de átomos. Una parte la bibliografía acá en este programa tenemos los datos que tenemos que no está dividido. Ahora hacen más cosas. Tenemos hace 2 o 3 años tuve un trabajo de guión especialmente que hice como dataciones, pero video exploración en unas fósiles caracoles, por ejemplo. Por eso es lo que es la verdad el depósito de ese cartón. Y con esto tenemos un poco más preciso. Ahora también vamos a dar un nivel de a veces tenemos como una precisión de más o menos 500.000 años, 1 millón de años. Falta poco la precisión hasta ahora. Y queremos trabajar, tenemos una nueva operadora en la ciudad que va a iniciar en septiembre. Estamos trabajando básicamente en un depósito que es la masa roja, que es un depósito que es muy común en diferentes partes de acá. El bonito cero, pero es como una cosa súper fundamental, no tiene muchas cosas. Queremos analizar las suelos, ¿no? Caliche, estas cosas, por mano tratar esta como citas si funciona para tener como una idea un poco más precisa sobre el tema. Por eso es claro, si no sabemos qué es el depósito, si tenemos el depósito, no sirve de nada.
Y en los caliches, ¿me explican cómo se le hace? Caliches.
Caliches.
Porque se generan es por el cultivo, ¿no? Pues,
Sí. Ahí te toca tu cultivo aquí, es muy y mucho más calor que, pues es como, sí, frío, sí, no, digo, son como más caliente esa zona. Pero hasta ahora, cuidado si esta funciona. Pero mucha gente está trabajando en calichos y con muchos problemas con la relación con plomo, con muchos problemas que no funcionan. Veamos si esta funciona. Otra cosa que trabajamos probablemente con estos procesos muy bajos de mucha grafita, hacer un monitoreo en gatita que estuvimos hablando la semana pasada. Como otro indicador, como por ejemplo, que es el dato. Durante 150 años de trabajo en los Alpes, de países ricas de Francia, Suiza, Alemania, Italia, etc. Y tenemos más preguntas que respuestas. Nunca paro. Siempre podemos hacer como otras cosas por ellos. Para tener como un par más.
Una pregunta, 2 preguntas, digamos, de los estimativos que hacen sobre el frío y caliente, están basados en el vino, y el polen del vino, los SAS que lo hacen muy propenso a desplazarse hacia zonas lejos de donde se
Sí.
¿Cómo logran separar esa señal de dispersión con local que está representando?
Sí, no, la idea es que me dicen los expertos de Porto. Dicen que normalmente es una de ellos que hacen con el polvo en sí, directamente, digo, algunas ponen en el río, están transportados afuera. ¿Sí? Entonces, nosotros buscamos por depósitos, es decir, depósitos muy finos. Por si tienes como corales, no funcionan los polvos. Entonces, con esos finos, depósitos de lagos, y al mismo lugar que hemos tomado también muestras de economía de lagos, composición del sedimento de las arenas, para saber la proveniencia de estos sedimentos. Y para saber que en verdad este viene de los Alpes y no de otras partes. ¿Verdad? Pero fuertemente las otras, tengo la mapa acá, las otras montañas altas que tenemos que existen antes son los Pirineos, que son más al sur. Pero las especies que vivimos por los extraterrestres son especies que vienen de los Alpes, y no necesariamente pero también por la televisión de la situación atmosférica que es muy del oeste al este, principalmente. Entonces, que los primeros tienen un poco más para llegar hasta el norte y después de pasar.
Y la otra pregunta, me acordé de un artículo que publicó Christine Bacon en el 2022 con Carlos Jaramillo sobre esta especie bien rara que está en el macizo de Santander, ahí, chica, mucho que se llama la ceiba barrigón. Y eso es un árbol rarísimo que crece en las playas empinadas y tiene un árbol o una barbita en todo lado. Y eso no está en China, mucho en México. Y la pregunta que ellos hicieron es: ¿cuándo apareció una ceiba barrigón? Y la respuesta fue mirando evidencias con materia que apareció hace 1.5 millones de años. Y la pregunta bien es: ¿qué fue primero? ¿Se levantó el macizo de Santander? El macizo de Santander está levantado en ese momento, la gran parte.
Sí.
Pero cuando calificó, entonces es una pregunta muy buena. Clave, porque ahí es donde uno podría separarla. También tiene la formación de la montaña, del clima. Esta planta es bien particular por eso, porque coexistió hace 1.5 millones de años con una montaña encantada, pero al mismo tiempo con enfriamiento, bueno, secado de los
Sí, sí, claro.
Entonces, ¿cuál es el que genera la especiación? ¿Cuál es el que genera la presión para esta planta? ¿El enfriamiento o el clima?
Que me hace siempre el mismo por ejemplo, en Chile.
Pero hay un pico de termoglobología como por 1.5 millones de años.
Sí,
Ese es el macizo.
sí. Tenemos, no directamente a Lorena. Sí, pues trabajo es serio, ¿no?
Y hay un pico de presión.
Sí. Digo, ¿verdad? Que cosas más vamos a la etapa de es como más un de esta. Sí, pero tenemos una indicación que no tenemos para cuando es conexión. Por esta, claro, tratamos solamente de eventos tectónicos, podemos a veces tener información. Pero de verdad, ¿qué es una altura? No sabes. Acá puedo ver relativamente, tuvo a 25 metros acá una resurrección que aumenta 2.000 metros de diferencia. Pero a 25 metros estuvo que no sé. Eso es lo que me preguntas.
Digamos, no piensa también el artículo de Jaramillo del 2006, muestra la diversidad de las plantas, el colegio, uno se da cuenta de eso, que hay una reducción de la diversidad desde el límite de Cretácico paleolítico hasta el Pleistoceno.
Sí.
Entonces, y el tratamiento del cariño también ha sido, bueno, que es tan importante es el levantamiento de las montañas, cuando la último pico de diversidad que tenemos en las plantas también es cuando tuvimos la migración y la formación del sistema de lagos europeos. Ese fue el último fenómeno que en realidad causó más que el levantamiento.
Es como que tenemos los datos. Sabemos que las montañas están acá y probablemente es una biodiversidad antes, pero si está la extensión, no tenemos ni la información de los elementos antiguos que tú puedes utilizar. A ver, no sabemos. Es claro, porque tenemos que las zonas más recientes es más fácil hacer la observación, es como el sample effect. Todas las aplicaciones que tenemos de evolución de las especies, sabemos que es la más y más diversidad más presente globalmente, como se llama nosotros. Pero muchas veces puede ser porque no tenemos los testigos de la actividad pasada. Sí, creo que es como uno de los límites, ¿no? Y claro, pues acá con esta temporalidad de eventos tectónicos y la especiación, pues es posible que es solamente una coincidencia, que no es verdad, porque tenemos que seguir un tectónico. Por eso necesitamos tener otras especies para hacer este test. No, creo que para hacer investigación hay muchas preguntas interesantes. Pero que es clave es la comparación con biología. Sí, los biólogos, ¿cierto? Sí, sí.
Pero creo que esto con lo permanente que es mirar la diversidad del suelo está relacionada con la diversidad de especies de plantas. Si tiene alguna relación que lo esté limitando, pues entonces no.
Absolutamente, claro. Porque claro, acá estamos hablando de unos suelos, pero suelos no son suelos. Porque va a ser la misma composición biológica o con tamaño raro, pero con la misma biodiversidad. Por el tenor de humedad un poco diferente, organismos por diferente. Por no tener la misma temperatura. Creo que es otra puerta de compensar, pero sí, investigación importante. Por el suelo es casi la conexión entre la biosfera o la atmósfera y la vegetación. Ese es como el punto que está siendo claro. Si en los suelos no tienes vegetación, ¿verdad? Solamente superpones árboles, mozos, esas cosas, pero todas las plantas arribas y muchos animales que viven también en los suelos. Claro, me parece un tema muy interesante, muy importante. Bueno, vamos a hablar.
Gracias a todos por la asistencia a este seminario. Y este semestre todavía no sabemos si programamos otra charla, pero lo estaremos contando por las redes y por correo. Muchas gracias a todos.
Gracias.